Hello, and welcome to this lesson on properties of similar figures. So we saw in the previous couple lessons that similar figures can be made using a dilation. And maybe we never actually called it similar figures. Um, we did. We said similar figures result from a dilation. We said that they're the same shape but a different size. It's like if one is bigger or smaller than the other. Um, we're going to look specifically at similar figures today in this lesson. And so, like, every one of these problems will have two figures or more that are the same shape but a different size. And then we're going to figure out if they're similar or not. Did you know that you make similar figures probably every day? When you have a picture on your phone and you pinch to zoom in or zoom out, the original image would be the pre-image. So like this would be like the original. After you've zoomed, the new image would be similar to the original. It's proportionally bigger. In fact, it says that here. It's the same shape. It's not distorted in any direction. It's just proportionally bigger or smaller. That's what makes it similar. Okay, similar figures are proportional. And that's going to be a big thing for us in this lesson. So you actually have a better definition. So the old definition of similar we had was two shapes that are this, or two objects that are the same shape but a different size. Okay, that's kind of what you first learn about when you first learn about similar figures. But we actually have a better definition now. It's two shapes that are proportional. That's key, that they are proportional. Because as that name kind of is going to tell us here, we can then use a proportion to do some math. So two shapes that are proportional and can be shown using a dilation and a rigid transformation like rotation, reflection, or translation. So the fact that a dilation happened and then maybe one of these other guys as well. Okay, they are proportional and it's the result of a dilation and potentially something else. Now, without even doing this, showing you how to do this lesson yet, right here, our goal is identify which shapes are similar. Be sure to explain how you know this is the correct answer. I bet right now I can say, okay, I want you to find which two triangles are similar. And you could probably do this right now. Think about it. Which of these two triangles, or out of these three, which two do you believe are similar? Most students say these two because they have the same angles: 55, 55, 35, 35, 90, 90. And they are absolutely right. So triangle LMN is similar to triangle RST. Triangle LMN is similar to triangle RST. And the reason why is because they have the exact same angles. But they have the same angle measures. And what that does for us, the fact that these three have the exact same angle measures means that they are the same shape. If all of the angles are identical, then these are the exact same shape. Just different sizes. I mean, this guy's clearly smaller than this guy. So that's the first property of similar figures. Similar figures have the exact same angle measures. All of the angles will be the same. The other property, the only other property, is the side lengths. Identify which shapes are similar. Be sure to explain how you know this is the correct answer. So this is a little bit more challenging. You can't necessarily just look at them right away and figure out which ones are similar. So what we can do, what we need to do, is set up a proportion. Our proportion is going to compare our triangles. So I'm going to compare these first two triangles, these guys right here. So the proportion I'm going to set up, the proportion I like to set up, is I'm going to set up this ratio compared with this ratio. Do you see how I'm picking the same two sides on both figures? That's kind of important. So I do 12 over 6 equals, so 12 over 6, 18 over 7. You have to use corresponding parts. So this 12 is kind of equal to this 18. They're in the same position on the triangle. This 6 is kind of equal to this 7. Now, from here, proportions. We've seen them before. You saw them a lot in 7th grade. What you do with them is you cross multiply. So we are going to take 7 times 12, 7 times 12, and that is 7 times 12, 84, I think. There we go. And then we're going to take 6 times 18, 108. And uh-oh. We just found that these are not in proportion. This cross multiply didn't work out. We didn't get the same thing on both sides. So I now know that those two, DEF and JKL, are not in proportion. So now you just have to do the proportion again. So we know it's not these two. Your other options are, it could be these two here or those two. So now you just set up another proportion and you try. So I guess I'm going to do this one first. I'm going to use those same two sets of sides. I like those sides. I use this and this. 18 over 7 equals 18 over 9. Now, working smart, not hard, I can see this is not going to work. There is no way that 7 times 18 is going to give me the exact same thing as 9 times 18. There's no way. 9 times 18 is 162. 7 times 18 is not going to work. 126. Not in proportion. Which means it has to be these two. So let's see. 12 over 6 equals 18 over 9. Cross multiply. Let's see, 9 times 12 is 108. 6 times by 18, I don't know. There we go, 108. That worked. That was the only proportion that worked out of all that we tried, which makes those two triangles in proportion. These two triangles are similar. So we should probably say that in our answer. So I'm trying to find a space to do it. You know what? Yeah. I'm gonna do it like over here, I think. Just have to squeeze it in. So triangles DEF is similar to triangle XYZ. There. So there's our answer. And there's all the work that we had to do to figure it out. Now, when you become more experienced with this, you can start noticing some patterns that make your life a little bit easier. But for now, it's really going to be kind of guess and check. All right, letter C. I would like you to try this one. So you have 3 triangles, just like we had in the previous problem. And I want you to figure out which 2 are similar. And if you take a little bit of time and look first, you might be able to get it right on your first try. You still need to do the proportion to prove it, but you might be able to find the right pair the first try. Go ahead and pause the video, try it out. When you're ready to continue, hit play, and we'll go through it together. All right, so if you looked carefully, the correct answer is these two triangles. And how would you know that just by looking at them? Well, if you take 8 and you times by 2, you get 16. 10 times 2 is 20. 4 times 2 is 8. So this triangle is just 2 times bigger than the small triangle. Or the reverse, it's times by 1/2. Remember how that's a result of a dilation? Well, if you took this triangle and you dilate it with times by 2, scale factor of 2, you would get this triangle. So we know that right from the very beginning. Now, I'm still going to do my proportion to prove it, but that's how you could tell by looking at it. In fact, this previous problem, the scale factor between these two is 1.5. If I took this, 6 times by 1.5, 1.5, I'm going to get 9. If I took 12 times by 1.5, I get 18. 10 times by 1.5 is 15. That's the scale factor that would be used to show that they are proportional, or to show the dilation. So here, I'm going to do this proportion. So again, I like picking those two sides, this and this. You really can pick any two sides you want. So I'm going to do 8 over 20 equals 4 over 10. 8 over 20. The 8 is kind of equal to the 4, same side. 10, or the 20 and the 10 are kind of equal to each other, same side. And then cross multiply. I can do that math in my head, 80. I can do that math in my head, 80. Check. They are proportional. Letter D. Same sort of deal, but now we've got 4, A, B, C, D. So it's kind of like a multiple choice. Now, I will tell you, there can be, and I think is, more than one correct answer. So kind of choose all that apply. So there might be 2 answers, 3 answers, 4 answers. So I want you to pause the video and figure out which ones out of A, B, C, D, which of these 4 down here are similar to this one up top. Okay? Go ahead and pause the video and try that right now. So, things that I would do right away. I noticed the angles. Remember the very first thing we learned about was the angles? 30, 60. If I could find a triangle with the same angles, well, I guess it would be 30, 60, 90. If I could find something with the same angles, it would be similar. And here he is, 30, 60, 90. So this one, letter C, is definitely similar, where letter B is definitely not similar. Okay, so we figured out the angles. Now, these two have side lengths. The way we'd figure out if they are similar to that is by using a proportion. So we're going to do that. Now, if you were, we should realistically try both because they both could be similar. So I'm going to do letter D first, and then I'm going to do letter A, just because I have space here. So sides, I'm going to use these two sides here. Now I have to be careful when I'm doing my sides of this triangle. I have to use the exact same two sides. So this is like, actually, I can make this easier for myself. I'm going to pick these two sides. This is the long side. This is the short side. I would have used like the short and the middle, but why not use long and short? So long side over short side. That means when I'm doing the big triangle, I can, or the original, I can use those two. Long side over short side. So make it easy on yourself. That's working smart, not hard. Make it easy to identify what side you're looking at. The long side, the short side. Long over short. Okay, now we proportion this guy. So 16 times 5 is gonna be 80. Yep. equals 3 times by 27.2. I know this is not going to work because there's no way a 3 times by 0.2 is going to end with a 0. It's going to end at 0.6 something. 81.6. Shucks. Didn't quite work. Okay. And we get to try again. Is letter A proportional? So I'm again going to use those same pairs of sides, long side and short side. So long side over short side equals long side over short side. When I cross multiply, 3 times by 40 is 120. I know that. And on the other side, 24 times by 5 times 5 is 120. That worked out. That is similar. Now, by looking at these two, we know they're similar. Can you figure out the scale factor? How many times bigger is the one than the other? The answer is 8 times bigger. 5 times 8 is 40. 3 times 8 is 24. 4 times 8 is 32. So there's a scale factor of times by 8. So that really, is this entire lesson. That's the goal of this lesson. The things you're supposed to learn is that similar figures have the exact same angle measures and their side lengths are proportional. You can use a proportion to check if they're similar, to see if they're similar. Now we do a couple application problems. James drew a triangle that has dimensions of 16, 10, and 20. 16, 10, and 20. I know, my 20 is not any bigger than a 10, but it's just a triangle. I drew a triangle, 16, 10, and 20. As long as you have them labeled, you're good. Janet drew a triangle that is similar, except her shortest side is only 6. So which of these, I'm going to make my triangle a little better, I guess. There. Which of these would I label as 6? Well, if Janet's shortest side is only 6, I'm going to put it here because that was the short side of James, so I'll make that the short side of Janet. What scale factor would be used to show that these triangles are similar? So think about this, maybe even hit some buttons on your calculator. What would you use to multiply this by to get that? Times by what? Guess and check is a good, valid strategy that works here. There's ways that are not guess and check, but see if you can do this. Can you find the scale factor? Just take a minute maybe. If you can't get in a minute, hit play and we'll go through it together. Okay, so check this out. 6 times by 1.5. That's not big enough. 6 times by 1.6. Not big enough. 6 times by 1.7. Too big. So you know it's somewhere between 1.6 and 1.7. 6 times by 1.65. Did it again. 6 times by 1.66. Now, I'm kind of getting a feeling here. 6 times by 1.66666666. Hey. So the scale factor is 1 2/3, 1.6 repeated. Now, that was using guess and check. We also could have done this another way. 10 over 6. The ratio, 10 over 6. 10, if I take 6 times by 10 over 6, that is the ratio of these two sides. That is the scale factor. we get the same thing. So, I mean, equivalent, which is also 1 2/3. So we can use the scale factor is just a ratio of the side lengths. So I could take this side and times by the ratio, by the scale factor, and get that one. I could also theoretically use that same information and find these sides over here. I mean, if I take 10 divided by 10/6, I get 6. I could take 16 divided by 10/6. I can find that this side is 9 6/10, which is 9 3/5. We don't need to know that, but I can. Once I know what the scale factor is, we can kind of convert from triangle to triangle. Letter B. Triangle ABC is similar to triangle LMN. Steve used a protractor and found the measure of angle A is 38. So I need two triangles. ABC, triangle LMN. Okay, measure of angle A is 38. Measure of angle B is 19. I'll move that 38 on the outside. Here we go. Using this information, is LMN acute, right, or obtuse? So, based off what we've learned so far in this lesson, this question is probably talking about the angle measures. Because we are given two angle measures, we know that these two triangles are similar, and we want to know, is this right, acute, or obtuse? So right now, we're missing this angle C. Let's find him, because I think that might be the key to our answer here. So background knowledge. All the angles of a triangle add up to 180 degrees. So 38 plus 19 plus something equals 180. You could figure out that something either mentally or by mathing. I like to do this. I would do 38 plus 19. That's 57 plus something equals 180. And then I would take 180 minus 57. Essentially, we're solving the equation. We're pretending this is an x, and subtracting that piece out. We get that is 123. So angle C is 123 degrees. Now, if these two triangles are similar, that means that their angles are exactly the same. So this would be a 38, this would be a 19, and this would be 123 degrees. So now the question says, using this information, is triangle LMN acute, right, or obtuse? Well, the naming of a triangle is always after its largest angle. This largest angle is obtuse. So this is an obtuse triangle. And if you don't remember what obtuse means, obtuse is a triangle that is open more than 90 degrees. The largest angle is like this. So if I drew this properly, it'd be wide open like this. An acute triangle is a triangle with the largest angle is less than 90. And we already know what a right triangle is. It has a 90-degree angle. Letter C. A group of 4 students was each asked to construct a triangle with angles that measured 42, 74, and 64 degrees. If each student makes their own triangle for homework, can we determine if they all will be congruent triangles? So if each of these kids made their own triangles and brought them in, would they all be congruent, or would they all be similar? Go ahead and pause the video. Try that on your own right now. When you're ready to continue, hit play, and we'll go through it together. All right. So They would not all be congruent. Congruent, again, means identical, twins. Well, imagine, I mean, you got a couple kids, and one kid comes and he makes his on a post-it note. So he drew his triangle on a post-it note, and it has exactly these three angle measures. Another student comes in and they have a piece of paper, and they drew it nice and big on that piece of paper. Well, those two triangles are not congruent. They're not exactly the same. If they have the same angle measures, as they should, they're the same shape, but look at them. They're definitely different sizes. If another kid, I don't know, like some kid who really wants to get extra credit or something, teacher's pet, comes in and he buys like one of those trifold poster board things and makes a huge triangle with the same angle measures. This thing's huge. Well, as long as the angle measures are the same, and it doesn't look like it in my pictures, but as long as the angle measures are the same, they are technically the same shape. They are similar, but not congruent. Okay? So as long as the angle measures are the same, they're the same shape, which makes them similar triangles, just like we learned in the very, very first problem of this lesson. So Lindsay drew a triangle on an airless balloon, so like there's no air in it. The triangle had dimensions of 24, 40, and 38 millimeters. She then inflated the balloon and measured the dimensions to be 65, 100, and 81 millimeters. Is the triangle on the inflated balloon similar to the triangle on the non-inflated balloon? I don't know. This one's for you. Why don't you go ahead and pause the video, try it on your own right now, maybe draw a picture if you need to. When you're ready to continue, hit play, and we'll go through it together. So drawing a picture is definitely helpful for me. I'm a big fan of drawing pictures. So the first triangle, it said had dimensions of 24, 38, and 40. Now when she inflates the balloon, I'm going to kind of keep these, like I'm going to put the biggest number, the 100, in that spot. This side is the smallest number, 65. I'm going to put them where the smallest number goes, and then that number was the one in the middle, and I put them there. So drawing a picture helps that portion of the problem. Now in order to figure out, it says, are the two triangles similar? Well, a proportion is the thing to do. I would use these two sides and those two sides because those are the two I really like to use. So I'd set up 24 over 40 equals 65 over 100. And then I would do a proportion. That is 2400. I know that already. I can do that math in my head. I cannot take 65 times by 40 as quickly in my head. 2600. So the answer is no, actually. Those were not similar triangles. And I mean, you could come up with the reasons, like maybe the balloon distorted the figure. Instead of it growing proportionally, it stretched one side out more than another or something. But according to the math here, they are not similar triangles. And we should probably say that. Is the triangle on the inflated? They are not similar. Boom. There. Now we have ourselves an answer. They are not similar. All right. Summary. In your own words, how can you tell if two shapes are similar? Go ahead and pause the video, think about it, put down an answer, some sort of summary. Okay, well, you can tell two shapes are similar if they have the same angle measures. That makes them the same shape. If their sides are in proportion, that makes them different sizes. They're in proportion. You know two shapes are similar if it's the result of a dilation and then potentially some other transformation like a rotation, reflection, translation. And that's how we do it. Similar figures are proportional with the same angle measures and are the result of a dilation. Okay. Thank you so much for watching this lesson on similar figures. Until next time, toodles.